When the some symmetry is spontaneously broken, then there is a topological defects that appear. And the one of the well-known topological defect is the domain wall, especially the broken symmetry was the discrete symmetry. But today I don't want to talk about some detail about some topological point of view, but instead I will focus how this domain wall can affect some cosmological implication. First of all, when the domain wall is produced after the spontaneously symmetry breaking of the discrete symmetry, this comes from some two degenerate vacuum. So some region takes some vacuum expectation value with the minus sign, and other region take the plus sign. That the boundaries of between the two regions correspond to the domain wall. And because the two regions have the different vacuum expectation values and the potential energy, like that. So the around the domain wall, this has some energy with some tension. So the surface energy density or the tension of the domain wall can be evaluated, which is denoted by the sigma, in terms of the parameters of scalar potential, like as lambda, which comes from the Cortic term of the potential, and eta, where eta means the vacuum expectation value. And by the dimensional analysis, surface energy density has the mass dimension of the 3. So the scale is proportional to the BAP cube. And one can evaluate the total energy density of the domain wall in terms of this surface tension by dividing the distance scale L. And by using the stress energy tensor of the domain wall network, then it gives the equation of the state, the relation between the project and energy density with the coefficients of the -2 observed. So the equation of the state is the -2 observed. This can be obtained by some align the domain wall to the just direction. Then the xy moment project and the z project has a precise sign. And if we evaluate this around the stress energy tensor, then we can obtain such a coefficient. And by inserting this equation of the state to the Bose-Friedman equation, then we can obtain the evolutions of the domain wall of the cosmic history. So the energy density of the domain walls changes proportional to the 8 to the -1. And the ordinary radiation and the matters of the universe component scale as 8 to the -4 and 8 to the -3 respectively. So the domain wall reduces more slowly. So at some moment, the domain wall becomes the dominate in this cosmic history. And such a domain wall domination makes some trouble. So that is called the domain wall problem. To evaluate the domain wall problem, one can consider how the domain wall affects some observational implication. The domain wall generalizes the Newtonian gravitational potential because it has this continuity. So For the gradients of the gravitational potential, the discontinuities along the domain walls are easily represented by the surface tensions and the gravitational constant. And we can obtain the gradients of the gravitational potential by integrating this formula, and the CMB anisotropy, the temperature anisotropy, is now proportional to the gradient of the potential. So the observation requires that the small anisotropy, there are upper bounds. So this constrains the surface tensions of the domain wall. So during the radiation domination era, the Friedman equations gives that the total annodances are reduced over the time, but the domain wall annodancy should be smaller than the total annodancy. So by using that, we can obtain the upper bound of the surface tensions of the domain wall. So by combining these inequalities with the anisotropy constraint, then to avoid the domain wall dominant, the domain wall should disappear before the time moment with the scale of the 1 over the g mu. So to satisfy this inequality condition, the domain wall should be the elinimate at the early approach or should be unstable. If not, the domain wall becomes a dominant component over the cosmic energy density, and this interrupts the cosmological history. So there are several mechanisms to avoid or resolve this domain wall problem. There are several types. The first one is inflationary delusions. If the discrete symmetry was spontaneously broken before or during the inflation, and never restored afterward, then all the pre-existing domain walls are inflated away. So the annodancy of the dW can be diluted. And this requires that the symmetry breaking temperatures, Tc, the critical temperature, should be larger than the relating temperatures of the inflation. But this concept is very simple, but usually the discrete symmetry breaking scale is not the inflation scale, so this is not our hope for the some physics model. The other way is making the domain wall becomes unstable. One can introduce the small explicit breakings for the system, then this leaves the degeneracy becomes a vacuum. So now the one vacuum has some slightly larger potential. And this makes the energy bias between the two vacuums. So the domain will experience some pressure difference from the one side to the other, so that this makes the collapse and the decay of the dW. The decay time is roughly given by the surface tensions over the energy difference. And this mechanism is widely adopted in the axion and the supersymmetry model. Why the axion and SUSY I will discuss later, because there are several domain will arise in such a new physics model. But such explicit breaking should be sufficiently small to ensure that the original motivations of the new physics and the symmetry. The other possible way to resolve the domain wall problem is a symmetry non-restoration at high temperatures. This means that even though the energy scale is very high, there was no symmetry. One can introduce the additional thermal corrections at the high temperatures. Then this thermal corrections makes the effective mass, especially the quadratic terms, are always positive. So the symmetry is restored. But when the temperature drops below the critical value, then the symmetry is broken again. So the domain was produced via such a keyboard mechanism with the thermal correction. But in the multi-scalar theory, the thermal corrections can prevent the symmetry restoration. So there are two scalar, pi1 and pi2, and thermal corrections now comes from the two different scalar. And by choosing some specific parameter regions, then the thermal mass term always gives some negatives quadratic terms. So as a result, the symmetry was already broken at the high temperatures, so never restored in the high energy scale. So this makes the domain walls never formed in such a multiscalar theory. This is a typical one, but the proposed by some new scenario. And the other possible way to resolve the domain problem is the light time entropy projection. Entropy injection from the light decaying particle from some scalar condensate or the model light particle. This can dilute the analysis of the DW. Now we turn to the why the domain problems arises in some specific new physics model. The first one is the supersymmetries, and the second one is the axion model. In the supersymmetry, especially the NMSSM, which is next to the minimal supersymmetry standard model, it contains additional singular S, and this has some exact discrete jet 3 symmetry for all the color superfield. So the sometimes forbidden, for example, the linear or quadratic for the scale and the mu term of the MSSM. And the mu terms are generated by the vacuum expectation values of the singular field S. So this becomes the dynamical solutions of the mu problem. But when the singular field get the BAP, the exact discrete jet 3 symmetry is now spontaneously broken, and this makes the topological defect, which is the domain wall. To resolve the domain wall problems arising in the NMSSM, one can introduce the explicitly breaking term for the jet 3 symmetries like as a higher dimensional operators in the superpotential W, like as a cortic term of the singular. This term leaves the degeneracy between the three different vacuum and introduce the Prauser difference over the domain wall. So eventually the domain wall decays and becomes unstable. The other possible ways is giving the additional correction terms like the thermal ones, but they have in this system during the impulations approach. Now we turn to the second new physics model. The axion also can arise the domain wall. Originally, the axions are introduced a strong CPs with the U1 PQ global symmetry. When the U1 PQ symmetry is spontaneously broken at the scale Fa, then now the complex color field can be written with the radial part with the broken scale and angular part. This angular parts correspond to the axion. And originally, when such a U1 continuous symmetry is spontaneously broken, the arised topological defect is the cosmic string or vortex, not the topological defect. But there is a QCD effect. Around the QCD scale, the non-perturbative QCD epochs explicitly breaks the U1 PQ symmetry to the discrete subgroup. So now the axion potential generates the instanton boom with the cosine periodic potential, and there is the domain wall number and the W, which is assigns the degenerate QCD vacuum for the instanton potential. This domain wall number and the W's is determined by the QCD anomalies of the Piquet symmetry. So the potentials looks like the periodic cosine potential, and each minimum correspond to the degenerate QCD vacuum, and the instant mean that the tunneling between the this different vacuum, and the domain wall numbers assigned each vacuum number. So the potential has and the W's number through the degenerate minima, and this makes the this degenerate vacuum makes the domain wall, and the surface tension has the order of the axion mass times the axion decay constant scale. So the problem is the axion with the electricity above to make the domain wall. For when the domain one number is equal to the 1, then the string has only the single one attaches. So the wall exactly on the poles has just order of the domain or surface density, surface tension. In this case, the network is unstable, so there is no domain wall cosmological issue. But when the domain wall number is greater than the 1, then there are the multiple wall, and they are attached to the each cosmic string. And now the both are balanced between such a multiple wall, so the domain wall network is stable and makes some cosmological issue. Sorry for that. The most common resolutions of this axion domain wall problem is also the introducing the small explicit breakings of the Piquet symmetry. For example, this makes also the potential bias between the different vacuum and makes the domain wall unstable. Also, the important remarks for the axion domain wall is when the Piquet symmetries are broken before or after the implantation. If the Piquet symmetry is spontaneously broken before or during the implantation, then the and never restored afterward, then the content fluctuation generated during the implantation in this isochromatic perturbation with the scalars of the Hubble. And these fluctuations make the isochromatic model constrained by the CMB observation. So the Hubble is strongly constrained, already we discussed it in the previous time. But in contrast, if the Piquet symmetry is spontaneously broken after the implantation, then this can avoid the isochromatic constraint. But now the domain of problems arises again. Lastly, as Bill remarks, not only the global U1 Piquet symmetry, also the global lepton number of symmetry can make the domain of problem. Similarly, they can spontaneously broken to some discrete symmetry. On the similarly, the QCD epoch, there is the non-perturbative, the electrologic epoch. So we can analyze with the similar instanton potential, and this makes also the domain wall problem. So today we talk about the cosmological domain problem, which is arising when the discrete symmetry is spontaneously broken through with that degenerate vacuum. And the stable domain wall generates the cosmological issue by interpreting the standard history. And there are several methods to avoid such a domain wall problem. Is making the explicit breaking to reduce the vacuum degeneracy, and the domain wall becomes unstable. And such a domain wall problems appears in the various new physics model, like as supersymmetric NMSSM with the discrete symmetry, And in the axion model, that you want pick symmetry with the non-perturbative case if axion is the addition allowed to discrete symmetry with the domain one number. Some models and considerations that are based on the following reference. The first of all, the first two papers, they're just historical papers for the domain one problem, and the next following papers discuss some resolutions for the domain one problems in NMSSM and axion, and some possible domain one problems in the left number.